Greetings at home students, this is Al Kessenholz. Today we're going to be lecturing about bubble and dew point, also touch upon glide. Now, traditionally the older refrigerants R12, 22, 134A, 502, R11, 123, they are comprised of different chemicals. When blended together, they form a new bond where you have one pressure reading equals one temperature rating. So on a PT chart, you have your pressure and one temperature. The 400 series refrigerants, 410A, 404A, 407s, the A, Bs, and Cs, they're near azeotropic. And what it is a combination of multiple different refrigerants in different proportions. And in doing so, they don't form a new blended refrigerant. Each one has its own characteristics that each chemical compound or each chemical refrigerant part of the mix will boil off at different rates and condense at different rates. 410A, we call it near azeotropic, but it only has about a 1 degree, 2 degree glide the most. And we never really concern ourselves too much with the bubble and dew point of 410A, but it becomes relevant when you're dealing with 404A, especially if you're going to do 407C, which is a replacement for R22. You can have up to a 8 to 10 degree difference in the glide. So we're going to go into that today and go through some worksheets here with this PowerPoint. So some of the reference materials and the credits that are due to ownership here that we have to give authorship to are as follows. We're going to be teaching from the Parker-Sporlin form 10-135. Recommend that you also download this document. It's a great form to learn from, and it's part of the second and third year curriculum. We are going to be teaching from the Sporlin or Parker PT chart, form number 1-619. I have a few extras laying around. The next time you come into class, I'll pass them out. It's a great tool. It has a little enthalpy chart on it, as well as some notes on some rules of thumbs on where to set up your low pressure controls or your sort valves to control off of back pressure. And I'm also going to be lecturing with the Danfoss Slider app. The one that I'm using for this presentation is going to be a PC-based version, but they also have an iOS and Android. And basically, it's a digital PT chart. Any of the other ones are just as good, whether you're using the Parker-Sporlin or the Copeland PT. That's fine. Just allows me to share my screen in Windows on Google Chrome, and it's a PC version. So this is what we're going to be going over today. This is part of the Parker handout. Notice that there's a form number on the side here, and it's a actual packet from Parker, and it's called Using a PT Analysis as a Service Tool. It's a really good write-up, and it gives us all the gauge pressures throughout the refrigeration cycle. That's the round dials with the numbers inside. That's if we took our gauges. That's PSIG, not absolute. And it also gives us the measured temperature of where the gauge is as well. So whenever we're doing a service call, what we have to do is not only take pressures, we have to take temperature. So you put your gauge on there, you mark down on a piece of paper, for example, the suction is 84 PSIG right there. And then you also take the temperature of that pipe. You take that 84 degrees and you look at your PT chart, and then you find out what the temperature is. But is it a bubble or a dew point? That's what we're going to find out, because it is a 400 series refrigerant, so it is a near azeotropic. First thing we want to go over is what is vapor. Okay, vapor is nothing more than superheated state of refrigerant. You can never have superheated liquid, and you can never have superheated saturation. You're always going to have superheated vapor. So everything in this diagram in black is represented as superheated vapor. So it comes out of the evaporator, superheated, it goes into the compressor, superheated, comes out of the compressor, superheated. We have to, in our mind, try to reprogram ourselves that heat is not necessarily hot to the touch. It just means that it's in the vapor form. It cannot stay in the saturated or liquid form because it's superheated past its saturation point. The other thing we have to understand is what is subcooled. Subcooled will always be in the liquid form. So we already touched upon heat being in the vapor form. Subcooled is going to be in the liquid form, and that's indicated by the gray color of the handout. And saturation has multiple different meanings. It's PSIG converted to temperature, and it's also a combination of a liquid and vapor state. It could be both. You could have 99% liquid, 1% vapor. You could have 99% vapor, 1% liquid. So on a PT chart, if you're looking at R22 and you say, okay, for R22, it is going to be, let's see, 60 psi, right? And we just go right to the temperature. It's going to be somewhere around 34 degrees. There's one temperature, one pressure. If we're dealing with 404A, we have two different temperatures listed for a pressure. It could be bubble or it could be dew. So this lesson is going to cover what we use for each one. So take a look at the diagram here, how it's laid out. We have pressures and measured temperatures, and we have to decide whether it's saturated, superheated, or subcooled, and by how much. So the first thing we want to do is we want to draw a line through the system. Okay. There's going to be two things that are going on. The left-hand side is going to be superheated vapor. So that's superheated vapor coming out of the evaporator, going into the compressor, and then coming out of the compressor in the form of discharge gas going into the condenser. The other thing on this diagram is subcooled liquid. That's after it comes out of the condenser, turned back into a liquid. And sometimes we have to add subcoolers to systems to bring it down even further. So sometimes the condenser can only condense it, but then there's other refrigeration devices such as plate and framed heat exchangers that allow us to subcool it even more. And there's even subcoolers that will go inside cases and refrigeration cycles to help take this suction gas that's already cool, even though it's superheated suction gas. It gets colder than the liquid going into the case, and sometimes they'll use that as a heat exchanger. That's why they'll take a liquid line and braze it to a suction line, so that it's allowing it to transfer the heat from the warm liquid line to the cooler suction line, and in doing so they get some subcooling in the process. So saturation is going to be PSIG converted to temperature. It's also going to be refrigerant in the vapor and liquid state together. So our evaporator is a saturation point of the system, the condenser is a saturation point, and even the receiver has a combination of liquid and refrigerant, and that's also a saturation point as well. We have it in the evaporator, condenser, and the receiver. All have a mixture of liquid and vapor. And you'll know that when you have 0 degrees of superheat, it's in that state where it's latent. There's energy being consumed, but it's in the form of latent energy, so therefore we can't measure it with a thermometer. There's not going to be any increase or decrease. So usually when you get your 0 degree superheat, subcooling, that means it's saturated. This should look familiar. This is on the Sporlan handout with the PT chart. This is an enthalpy curve, and we have what's known as the bubble point and the dew point, and depending on where we are in the system, we have to know which point of the PT chart we're going to use. So dew point is pretty simple in the fact that it tells you to determine superheat, use the dew point. It tells you right down there in little letters. So just note that dew per heat, that's another way of trying to remember it, dew per heat. So dew per heat, or dew point, is going to be on anything that is superheated vapor. I'm going to use the dew point on the outlet of the evaporator, to know what my TXV superheat is. I'm going to use dew point on my inlet to my compressor so I know what total superheat is back to the compressor. And I'm going to use dew point on my compressor discharge so I know what the superheat of the compressor discharge is. All going to be used with the black dew point as known as on the PT chart from Sporlan. If we look at the Sporlan chart here, and if this is 404A, the dew point is also going to be in the black numerical values there. So that's one way to find it. It's going to be superheat is going to be in the black ink. The reverse is true when you want to know what your bubble point is. Your bubble point is subcooling, anything that it has reached its full potential and condensed from a vapor to a liquid. Now, it also tells you to determine subcooling, use the bubble point. So we also call that bubble cool. That's taken off the internet. People are using that terminology now. And that's used at the outlet of the condenser. It's used to the inlet of the TXV. Right, that's all going to be your bubble point. Notice that bubble point on the Sporlan PT chart is in blue. So if there's one thing that you walk away from here is the blue ink means liquid. Blue is liquid, and if you're trying to find the PT relationship for liquid, you're trying to find the subcooling temperature of that liquid. So whenever we're using anything on the condenser, the receiver, the TXV, all right, we're going to be using the blue side of the PT chart for bubble cool. Blue is liquid. So hopefully that's helpful. What we have in your coil now is a glide, okay? And it's also going to have a saturation point where when the refrigerant goes in there, it's going to either boil off or condense at different rates. Remember that the refrigerants are made up of multiple different refrigerants, and each one has its own boiling and condensing point. So it is possible to have both vapor and liquid together in the receiver. This is also known as fractionation, but it's also at the saturation point of both being a liquid and a gas at the same time, as long as there's liquid on the bottom of the receiver where we could push it out to the system. So what we have to do with this chart here is we have to take a pressure and we have to convert it to a temperature. That's number one. So what I recommend doing is using the Danfoss slider app. So if the condenser here is at 312 psi for 404, right, we're going to come over here. I'm going to go to my Danfoss slider app. Just remember that you have to be in either gauge or absolute. Make sure you're in absolute. Make sure you're on PSIG. Over here on the left-hand side of the Danfoss slider app, it's pretty neat. It tells you the chemical composition of formula. So there's 44% of R125. There's 52% of 143A, and there's 4% of 134A. And if you notice that these are three separate refrigerants at three separate proportions, so therefore this is what causes the glide. All right, each refrigerant has its own boiling and its own dew point. So the difference of the two is the glide. So if I said that there was, how many pounds was in that condenser here? 312. There was 312 psi in that condenser. All right, that equals 120 degrees for my bubble, and it reads 152 degrees. So let's see what we got here. We have do this again. 312 psi. Bubble is 120. If it's dew point, right, we're still at 120, so that's good. All right, so do we choose bubble or dew? So dew per heat is for the suction side. Bubble cool is for the liquid side. So I'm going to go to my bubble slider. I'm going to type in 312. Once I type in 312, I get 120 degrees. I go back to the slide here, and the measured temperature at the coil is 120 degrees. So the pressure converted to temperature is also 120 degrees. So when we do this, we have a saturated coil, right? Because our pressure converted to temperature is 120 and our actual line temperature is 120. We have 0 degrees. If we come down to the condenser here, right, 292, going down to the receiver, we have a pressure drop. So we're going to have to go back to the Danfoss slider app, and we're going to pick 292. We're going to stay in the bubble scale because we are still in the liquid side. 292, and that's 115 degrees converted. So we're taking PSIG gauge, converting it to temperature using the bubble. Go back to here. And look at that. Our gauge converted to temperature is 115. Our measured temperature is 115. We have no superheat. We don't have any subcooling. The difference is 0. We're still saturated. Okay, so we're saturated in the condenser. We're saturated in the receiver. Now that is possible. Right? We're letting the numbers speak for ourselves, because when you go out in the field, you have to take both the gauge pressure converted to temperature, and you got to take the actual probe temperature of the pipe, and you have to determine what's going on in the system. Even though we're running a sample here, right, our feelings don't matter. It all depends on exactly what we're getting. Mathematically, we're going to let the numbers speak for themselves, and it's going to tell us what's going on in the system. This is how we're troubleshooting. Now we come down a little bit more, and we're 292. And we know that 292 is 115 degrees because we know that from the last time we ran the equation. We're still 292. We convert that to 115 degrees Fahrenheit on the app, but we measure 110 degrees Fahrenheit. So what just happened? What happened is we have a 5-degree difference, right? Our measured temperature is actually lower than our gauge pressure converted to temperature, and doing so we have a 5-degree subcool on our liquid line. We go down a little bit further in the system, right, and we have 273 psi. So we got to take that 273 psi and we have to convert it to temperature. So 273, convert it to psi. And that equals 110 degrees. And we're going to stay in the bubble because we're on the bubble cool. We're on the liquid side. So 273. Gauge pressure is 110. We'll come over here. Our measured temperature is 102. Remember, this was 110 converted. So how much subcooling do we have here? 110. Right, subtract 102 is 8 degrees. So we have an 8 degrees subcooling. Now, it doesn't matter which number is on top, which is on bottom. It's the difference of the temperature. There is no negative subcooling. There is no negative superheat. It's just that you did the math improper. So all you do is you take the larger number, subtract it from the smaller number, and if you do it with the calculator and you get a negative integer, the negative doesn't mean anything. It's the difference of the two, and it's either going to be the difference being superheated or its difference going to be subcooled. So anything on the liquid side is subcooled. Now we go into the evaporator. The evaporator is 87 pounds. So we're going to go and convert 87 pounds with the refrigerant slider app here. We're going to go PSI to temperature. And it equals 40 degrees, 40.6. So we'll go back to the PowerPoint. 86 converted to temperature. And at this point, we're starting to flash off. So we should start to use the duper heat setting. So I have to go back here and change it from bubble to duper heat. And my duper heat is, the gauge pressure is 87 psi. All right, and that gives me about 41 degrees. You know, see how there was a difference? One was 40, one was 41. So this is the one I have to go with, duper heat, because I'm starting to boil off. I'm going into the evaporator. Glad I caught that. So 41, and the measured temperature is 41. I have 0 degrees difference, so I'm not superheated, I'm not subcooled. What I am is I'm a mixture of vapor and liquid together. I'm saturated. So that's where I need to be. Now I want to know what is leaving the coil. This is going to allow me to adjust my expansion valve to make sure I have the proper superheat for my expansion valve. So I'm 84 psi. Go back to the Danfoss slider app. And we're going to stay on the dew point because we're on the vapor side. And we're going to hit or enter in 84. And I'm 39.2. All right, so I'm just going to round that down to 39. Be easier. Go to the PT chart. And out of the PT chart, our gauge converted to temperature on the duper heat scale is 39. So our difference between our saturated PT and our measured temperature of 49, we increased 10 degrees. I have a 10 degree superheat. That's where I would adjust the expansion valve. So as of now, 10 degrees is what our target is for that expansion valve. We're going to leave it where it is, and we're going to follow the suction line down to where it goes into the compressor. So this would be, we measured TXV superheat. Now I want to know what total superheat is back to the compressor, which is important. It affects the cooling of the compressor. If it's a semi-hermetic type of compressor that draws refrigerant through the motor windings, it has to be set up for compression ratios, so on. So we need to know what the total superheat to the compressor is. So we take the 84 psi, which we already know the saturated temperature is 39 degrees on the duper heat scale, and we take a probe and we measure the pipe, and the pipe is 60 degrees Fahrenheit. So we have to now find the difference between 39 and 60, and that difference is 21. I am superheated, all right, 21 degrees going into my compressor. Even though it's 39 degrees and the line is sweating and it has a whole bunch of, the end bell, the compressor is nice and cold, it's sweating, it's still in the superheated form. See, superheat is not a bad word. Superheat is not, you may not get burnt by superheated pipes. It's just the state of the refrigerant. The superheated past the saturation state. It can't stay in the liquid or vapor form anymore. So it goes into the compressor, right, at 60 degrees Fahrenheit, and it goes in with a superheated temperature of 21. The compressor, right, turns into a high pressure, high temperature gas, still considered superheated, but it's 312 pounds psi, and it's also 210 degrees Fahrenheit when we measure it on the pipe. So we go and we figure out what 312 degrees is on the Danfoss slider app. It's 312 psi. It should be 120 degrees. All right, that's the saturation point using the dew scale, duper heat. All right, but we know it's not 120 degrees because the heat of compression. So we go back to the PT chart, and we take that 312, which equates to being 120.5, and we have to subtract it from the measured temperature of 210. So we're left with a superheated vapor of 89.5 degrees Fahrenheit. So it goes into the condenser superheated 89.5, and then we repeat the process all over again. At this point, this is on the Doppler heat scale. As we go into the condenser, we now go and change from Doppler heat to bubble cool, right? The liquid, when it gets condensed down as a liquid, we use the bubble cool scale. For extra help, I highly recommend that you visit these links. There is the Sporlan video on YouTube on how to use a PT chart. It's basically what this lecture is, but with Sporlan's graphics and their way of explaining it. There's a little bit more now with the Sporlan on classes. They have another video called In-Depth How to Use a PT Chart. And highly recommend that you watch this video, Saturation, Superheat, and Subcool. I hope that you found this slideshow helpful. I will link the PDF to this PowerPoint in the folder so that you could visit these links for your own resources. Thank you so much. I'll see you back when you return in person for class.